Okay, I suggest we start the second half of the session. It's kind of my hint. Okay, I guess this will do. So the first part was, important topic was sustainability, and we looked into energy. We looked into carbon print a little bit as a side effect of that as well. And this is how most people look at sustainability. Like energy, we have to optimize, and then everything will be good. However, we often overlook other important aspects. And in this specific talk, we will cover water. And water is equally important when we speak about sustainability. And moreover, if you look at the report of United Nations, again, I'm just quoting, like the next war will be over water, because apparently water is the most scarce resource on Earth, more scarce than energy and things like that. Apparently we have abundance of energy and heating and stuff like that. Anyway, my point is that we have another important look at sustainability from slightly different perspective, and of course not specifically on water, but a view and look of computer scientists on how we can do and help with the water domain. Victoria, stage is yours.
Thank you.
Can you hear me? Yes. Okay. Thanks a lot for the introduction, Alexander. I'm Victoria from the University of Amsterdam, and I'm in a very privileged position because yesterday we had 2 hours of talks about digital twins, so now you know all the basics about them. I can skip them. And instead I'll start immediately to describe you how our journey, how we approached engineering a digital twin of a critical infrastructure. So what is a critical infrastructure? You can think of a water distribution network, so delivering drinking water to people, but I will also cover topics of wastewater collection. I will cover a little bit about energy. You can also think of a transportation network as a critical infrastructure, but I will not be touching that type of infrastructure in this talk. And when we're thinking of creating digital twins of such infrastructures, right, we need to think about this sensor actuator loop that most of you are very much familiar with. We need to understand the environment, we need to be able to interpret it, to understand what is going on, to analyze it, and then to be able to make decisions to optimize the environment according to whatever goals we have. There are a number of challenges for critical infrastructure, and sustainability is one of the important ones. The main goal of the critical infrastructure is to do what it was designed for, right? To deliver water to people, or to collect waste, or to deliver energy. But usually the second goal of such an infrastructure is to do it in the most efficient way, because we are talking about a large-scale, geographically distributed, huge systems that consume a lot of our resources. Another important challenge for such infrastructures is partial observability of the environment. You'll be surprised how much, how little we know about little parts of the systems, even though the systems are designed to be to operate for people. Usually, we have a lot of knowledge about how the system operates on a large scale, but for example, even in a water drinking network, if you look at all the pipes in the physical network, a lot of them are not directly observable, so understanding what's the pressure of water at this particular location, or what's the flow of water, what's the water quality at this location, is not such an easy task. And in case of wastewater, last year there was a new EU regulation directive that requires wastewater companies to monitor much more precisely wastewater that goes into nature and treat it, because in case of extreme rain events, sometimes not all water can be processed by wastewater treatment plants, and then it goes to overflows, then it goes into nature. And up until now, even in the Netherlands, where there is a very good monitoring system for wastewater, there was no precise monitoring system that would tell you exactly how much water goes into nature and treated. But now we need to have the system, so this is one of the things that we're ensuring that we will be able to measure it much more precisely. Another problem is a data drift, where we know that environment is not static, right? We build a system under some assumptions, and then those assumptions change, and the system that we build is no longer optimal for whatever it is designed to do. So we need to be able to detect it and analyze it. And finally, interpretability is a very important topic, because even if we construct very precise machine learning systems that tell us, let's say, that can predict water pressure in a certain state, if something changes, let's say our simulations do not correspond to the sensor data that is given to us, we need to be able to understand what is the cause of change. So we need to be able to interpret it and explain it in a human readable manner. So my talk will be mostly about the DITEC project that we're working on for the last 3 years. The project is called Digital Twin for Evolutionary Changes in Water Networks. Here every phrase is important. We are building a digital twin, so we would like to estimate network conditions. We would like to be able to know exactly what is going on in our whole network at any moment of time, in real time, and we are basing our estimations on minimal external sensor information. We want to be able to reflect changes in the network in real time, and mostly we're using deep learning for state estimation. I will tell you more about that. Now we are looking at evolutionary changes in the network. So if there's some change, for example, a leak develops, or a behavior of people changes in terms of how much water they consume, or a valve is broken, so water goes into part of the network where it's not supposed to go, we need to be able to detect it and alert engineers about it. And more importantly, we need to be able to reason about this change and interpret it and provide explanation in a human understandable manner. And finally, our pilot is in Oosterbeek, Gelderland, which is in the Netherlands. We have around 7 years of sensor data there, but as you will be able to see later, the sensor data may not be sufficient to do everything that we need. So ideally, this is our water network, and ideally we have sensor coverage that covers every little node in the network, right? So then we can measure directly what is going on, what is the pressure, what is the flow, and then if something changes, we immediately detect this change by sensors. But in reality, we only have very few sensors in the network. Why? Because installation of the sensors is very expensive. Pipes are underground, so if you put a sensor, you need to put it when you initially lay the pipe, or wait for 10 years for maintenance. If sensor breaks, there's nothing you can do. So there's very limited locations where we can get information directly from. So what can we do? Traditionally, there is a lot of hydraulic simulation tools, right? Mechanistic models. They are very precise for water distribution networks because they are closed networks, so they, let's say, you can describe the behavior very well with physical laws. The problem of mechanistic models is that they require a lot of calibration. They require a lot of knowledge about, let's say, the initial state of what is going on in the environment. So there's a lot of parameters that you need to define in order to be able to run your simulation. If you define those parameters correctly, then you run your simulation, and then you have the description of how the water network will behave for the next, let's say, day or several hours. But if something is wrong in the parameters that you define, then your simulation is wrong. And that's why a lot of water engineers spend a lot of time on recalibrating their simulations whenever something changes in the environment. So we want to avoid it. There's a lot of parameters that they need to think of. We want to avoid it by creating deep learning reconstruction models that can look directly at the sensor data, even if minimal, and say, okay, there's some change in the sensor, so it must be a change in the, it must represent a change in the environment. So now we want to know exactly what was changed in the environment. And instead of running the whole simulation, we go directly from our minimal sensor data to knowing the whole network state. The problem for deep learning state estimation is that it needs to be trained. And to be trained, it needs data. So where do we get it? You already know that we only have very minimal sensor data, right? It's not all network that is covered by real sensors. So, and even if we look at historical data, there is only so many different situations that we've seen. Of course, there's always some anomalies, there's some leaks and so on, but maybe tomorrow there will be another leak that is developed which looks a bit different from the one that was yesterday, and then our deep learning model does not know about it. So using real sensor data that we get from the environment is insufficient to train these models. So how can we solve this problem? We have our hydraulic simulation tools, we have our mechanistic tools, and we can use them to augment the data that we have. So this is what we've done. We had topology of a network, which is like a description of a static graph of how the network looks like and connections and all the attributes that we care about. We had a lot of parameters to change, like elevation, like connections, pipe lengths, pipe roughness, and so on. And we ran a lot of simulations under different conditions, under different demand patterns, under different rain patterns, and so on. And we created a huge synthetic data set of different scenarios. And then we created our deep learning model based on graph attention networks. So there's a number of layers. Each layer updates their weights based on the information from neighbors. The way we trained our model is that we masked most of the nodes in the network. So we split the data set into snapshots. You can think of, you have a scenario, right? The scenario is maybe 24 hours of a simulation. So you split it into 15 minutes or 30 minutes or 1 hour, and then you have a snapshot of a network. And this is a single data point that we can input into our deep learning. And then we only left unmasked 5 to 1% of the nodes. So we assume that our sensor data covers between 5 and 1% of the network, and the rest, 95 to 99, are invisible to us to measure directly. And obviously we try to reconstruct then the network. And it worked. There were a number of approaches that tried to do similar things before us, and in case of our architecture, we managed to achieve much lower error rate with reasonably low number of parameters, so it's also efficient to train. And what I wanted to show you is an example of result for like 2 different nodes. Here you see 3 lines. Oh, maybe you don't really see them. I will have in the next slide a bit close up. One is what the initial simulation shows you. Another is what the deep learning model shows you, and a third is the raw sensor. So you can see they, in principle, follow each other very well. So we know that, okay, our deep learning model can reconstruct the whole network, even based on minimal sensor information. But what you can see is, so the deep learning model is green and the simulation is red, and the raw sensor is blue. And obviously you can see that deep learning model learned to reconstruct the simulation, not the real sensor, right? So as long as the simulation is accurate, we can use it for reconstructing also the real environment. Which, by the way, I forgot to say, so here the validation was done on the real data from Osterbake network that we've done. So we trained it on simulated data, but we tested it on the real data from the real network. And one more thing that I want to say here is that we spent a lot of time on creating this data set. It was a lot of work. And when we started reading papers about people doing this, let's say, water research and doing all these simulations and so on, in all of the papers, what you start with is that people do the same simulations as we've done. Whatever thing they need to do, if they do state estimation or demand forecasting or any other thing, they need to create the data set first. So every water researcher would use the same simulation tool as we used, would create some data set for whatever parameters they need, and then they would use it for their research. So it's all like, okay, we already spent a lot of work on that, why don't we make this data set available? We looked at what other data sets available for public, and there was only one in 2018. a very small one on a small network, a part of Hanoi, Vietnam, a network with 32 nodes and 4 adjustable parameters. So the data set was actually very small, and even though it was so small, it was used in many papers as a data set for testing their solutions, because it was the only one available. So what we've done is we published our data set as initially on the node as a small scale, and then we understood that it's actually very useful thing for many people. So we spend much more time to generate a proper large-scale data set that water researchers can use for different tasks, for creating foundation models, for creating surrogate modeling, for state estimation, demand forecasting. So we found basically all publicly available network description of water distribution networks. We started with 66, but some of them were having problems, some of them were duplications of each other. So we ended up with 36 publicly available networks, and we ran simulations for all of them under different conditions. We considered 38 different hydraulic parameters. Remember that here it was only 4. And then we ended up with millions of different network states that we published as a data set on Hugging Face, so it's now available. And we have a preprint, it's still under revision in, as a publication. And the main goal of this data set, as I said, to be able to train for many different tasks, not just a single task. So our vision here is that we can use it for training water foundation models. So if we pre-train a general water distribution network model based on all these different networks that we have, and then we can fine-tune it for state estimation, state sensor placement, leak detection, and any other task you may have. Now, we had this whole pipeline that we used for creating the state estimation for water drinking networks, and now we wanted to see whether we can recreate this pipeline in a different domain. And if you look at the pipeline, you can see that actually the whole pipeline consists of collection of small steps which are very much interchangeable with each other. So we can just exchange the, for example, simulation service that we had with another service, with another simulation from another domain. And this is what we've done for a wastewater collection system. Now, wastewater collection has water name in it, but it is the only thing that is similar with drinking water networks. Because it's a collection network, it's not a distribution network, and the wastewater characteristics are completely different, but also the network is organized differently. You no longer have like pipes, instead you have like this underground sewer highways that collect water, and in many cases there's like overflows that where water can go basically outside of the water treatment network in case of floods or anything. And there's many more parameters that like outside external parameters that affect the behavior of the network. So if drinking water network is a very controllable system, the simulation is very precise. In wastewater collection, your simulation operates under a lot of uncertainties. So even wastewater engineers, they basically work with like uncertainty and risks, and they say, okay, we need to estimate water level within 20 to 50 centimeters, and then we are fine. So this is what conditions that they have. So we basically we took the pipeline that we already had and started exchanging the services around, right? We now had a different simulation tool, InfoWorks for wastewater. We again had a different topology. We basically recreated a synthetic data set in a similar way, but now obviously for wastewater, and created the same snapshots and used the same architecture that we used before. And then managed to create the same model for state estimation for wastewater. But in this case, as I said, because of the many more external parameters that you can have, you can see that the lines don't follow each other as nicely as they were following each other for drinking water network. And we managed to achieve the acceptable results, acceptable for water engineers, so within this 20 to 30 centimeters. if we have 30% coverage rate of direct sensors. Okay, so this was one thing, but now I want to talk more about the selection of models in production. So while doing all these things, we had a lot of different models to test. And sometimes what we have is different state estimation models, and not a single one of them dominates all others. So for some state estimation models, they would get better results under some conditions, but other models will get better results under different conditions. So what we want is to be able to run a model in production that is always outputs us the best estimations under the conditions that we currently have. And how can we do it? So the way we approached it was by basically building, I wanted to, first to show you an example. This is an example from the energy consumption data set that we took from Kaggle. So what we've done is we took 3 best performing models that perform a next state forecasting for the next hour of energy consumption. And we also create 2 ensemble models out of the 3 that we took, 3 best performing ones. And this is the absolute error of energy forecasting, as you can see. And even ensemble models don't produce the best results. So you can see that sometimes one model dominates, sometimes another model dominates, depending on whatever other factors we may have. And in this case, what we can have is we can build this adaptive model selection mechanism, which works as follows. We have the production system that runs the best performing model at the time. For us, we have, because we're doing next state forecasting, it's an advantage for us because after 1 hour, we know the ground truth of 1 hour before. So we can estimate how well the models are performing at the current moment of time. So one model runs in production and outputs us the best results for estimation, and the rest of the models run in an ephemeral what-if environment so that we can estimate the performance of other models as well. They don't need to get the same sources as the production model. They don't need to get all sensor data as the production model, but we only need to run for a subset of data to understand their performance. And then as soon as we see that one of the models in ephemeral environment starts performing better than the one in production, we can switch. For the energy data set that I mentioned, because we didn't have a dominant model, we managed to achieve quite good results in terms of the total error. And we also tried it with the models that I talked about for drinking water network. But here, in fact, what you can see is that we did not manage to achieve improvement compared to, let's say, the static model selection, because the gut model that we constructed was a dominant model. It was always producing the best results. So the adaptive model selection in this case wasn't very useful. The last topic that I want to cover is the explainability. I already told you that it's very important when we have a change in the environment to be able to kind of look at it critically, see like, okay, where is this change coming from? How can we explain it? What can we do with it? And so on. And if you start looking at raw sensor data and you say, okay, this sensor shows you this value, is this high, is this low, what does it mean for other entities in the network? You don't have this information readily available to you from your raw sensor readings. So instead, we investigated using ontology and ontological description of a water distribution network for trying to get to explainable results and explainable let's say, rules of what changes in the system. A brief reminder, but we already had a lot of ontologies mentioned in the previous talk. Ontology is more like a class description and the description of potential relationships between different classes. And when we're talking about knowledge graphs, we're talking about a specific instance, a specific water network with specific pipes and connected through junctions and pumps and so on. So we performed a literature review before we started doing this to see how ontologies are already used in digital twins. from the already 2 years ago, this review was, and you can see that very similar to the figures that we've seen yesterday. There was almost no usage of ontologies before year 2020 in digital twins, and then 2021, 2022, the papers just skyrocketed. But also, obviously, because the usage of digital twins skyrocketed. And we looked at like a reference digital twin architecture. So usually you have physical layer, layer of communication, a middleware layer. Then you have a digital layer that has all the, let's say, logical notions of your environment that processes the sensor data, and then the application level. And then you have the organization level that manages the whole digital twin. And what we've seen is that ontologies are being used in all layers, but mostly in the physical layer and digital layer, which makes sense because these are the layers that have environment representation, either raw environment representation on the physical layer, or let's say high-level logical representation on the digital layer. And there are a lot of ontologies also having a connection between two layers, but also between other layers. Now, the problem that we had was that there was no ready-made ontology for water drinking networks, so we had to create our own one. We looked at existing methodologies of ontology creations. There were a number of them, so we looked at their characteristics, like how time-consuming they are and so on. Most of those methodologies for ontology creation were developed for manual ontology creation, right? So they provide you the steps on what you need to do as a domain expert to create an ontology in a certain domain. We chose upon life ontology construction methodology. It was very well described, it was very specific, very every step was following a clear algorithm and so on, so it was very easy to use. But instead of following it ourselves, we obviously asked LLM to perform these steps for us, and in order to give sufficient information to LLM, what we've done is we used the documentation of simulation tool that we used in the past for dataset creation as a document to tell LLM about the domain that we're having. So, and we managed to create ontology, not immediately very useful, so we had to have a couple of iterations with water experts to arrive to a final version that we were happy with, but we did it. And we published also like a Python package that we can use files that are usually used to describe water networks. Now we can use them to create knowledge graphs for these files according to the ontology that we created. And how do we use it? So we use it to extract semantic rules that describe system behavior. On the one hand, we have the sensor network that senses information from our water drinking network. We have this raw sensor data that's from every sensor, just a list of values, list of measurements that don't tell you much. And on the other hand, we have the ontology that describes the entities and relationships in the network. So when we combine them together, what we do is we use associative rule mining, which is a data mining approach to extract rules from the environment. And if we don't have any semantics, if we don't have any ontologies, what we have is rules like this. If sensor 1 measures V1, then sensor 2 measures V2. So rules can be a bit different, but as you can see, they don't tell you much unless you're, like a water expert that immediately already has in their heads what all those sensors mean and what it means to have this measurement. But if we semantically enrich it, then the rules that we have are more in the form of like, if a flow sensor placed in a pipe with this lens measures V1, then the pressure sensor that is placed in a neighboring junction measures something else. So you already see that basically the rule describes you like a little bit of a situation that happens. So it can be much more useful. Now, what we've done is we created a new rule learning method that is also based on deep learning, based on autoencoder. So the way it works is, on the one hand, we have time series data, time series data from our sensors. On the other hand, we have the created knowledge graph, and we perform binding. So we perform a binding of sensors with the entities in the knowledge graph that we constructed. So we have semantically enriched data set, where every measurement is enriched with semantic information, with its attributes of the local situation. And then we feed this semantically enriched data set into autoencoder, and the goal of autoencoder is basically to extract patterns of the environment behavior, right? Because in the we feed every single situation in it, and because of the autoencoder properties, what we when we try to train on reconstructing the situations, what we get at the end is patterns of the commonly seen relations between sensors. So once we train this autoencoder, we can then ask autoencoder, please tell us what else is happening if we see this and this situation. So we can say, okay, if you know that some sensor measures this and some other sensors measures that, and there is this connection between sensors, what else can you tell about the situation? And it will give us the answer. We had some, we've done some tests, obviously, on this rule learning pipeline, and the problem with rule learning is that it's very hard to know when rules are good and when the rules are bad, because you have a bunch of rules. How do you decide whether they are good or whether they are bad? There is a number of rule quality metrics like support, confidence, lift, jumps metric that basically tells you how interesting this rule is, so how statistically important this rule is, and so on. We needed to kind of have one number that would tell us whether the rule is good or not. So what we've done is we apply those rules on downstream classification tasks. It's basically like you learn a bunch of rules, and then what you want to do is that you pick a label that you want to extract from the rules, and then you use those rules in classification for that label. And then we compared our algorithm with exhaustive algorithms like FP-Grows that exist, and managed to basically achieve the same accuracy while having considerably less rules and finding them in considerably less time. And we also compared rules that we could extract with semantics and without semantics, so with this ontological information versus just using rules based on raw sensor data. And in fact, semantics helps, like if we use our IRL approach, autoencoder approach, we again find considerably less rules than we would find otherwise, while those rules have a higher support and confidence metric, and they cover a higher part of the data set. So to summarize, that's all that I said. If we put together the different approaches that we investigated to make this digital twin of our water drinking network operational, we have the physical environment and we have the data preparation. So we have a number of data sources. We have our sensor data, which comes directly from sensors that we have in the environment, but we also have the description of the network, which provides relationship, and it's very domain specific, which we then transform to a knowledge graph to extract the semantically valuable information. And then we have a number of learning and reasoning modules, rule learning, change detection. We have physical simulations that we all use for performing real-time state estimation on the network. And then we can also use it for running different what-if scenarios. So what if something changes, what if something else changes, and so on. And then we have all of this we use it to build a digital twin. And then we also have the decision-making module that, first of all, performs adaptive model selection that I mentioned based on the information that we get from the accuracy of modules. And then it can also perform alerts and dashboarding for people who want to monitor the environment. And then it can perform orchestration for the digital twin itself, but also for the environment, in case there is orchestration of the environment. And those are some of the papers that I was mentioning during the talk.
Thank you. And now time for questions.
Thanks for giving your insights in your work. You particularly focus on ontologies and knowledge graphs. From my understanding, in many domains, it is also necessary to have an understanding of the workflows and processes which are going on. Do you already think about how to enhance a digital twin with process models or workflow models and things like that? Or do you think just ontologies are needed?
Yeah, so I have to say, in our case, there is a huge emphasis on state rather than the process. Also, in the first part of our, since I was talking about state estimation, so what is going on at the current moment of time. The process in our case, we don't really we don't consider the process, but what we do consider is we consider the temporal relationships between, let's say, conditions of the network over time. For example, in the next state estimation, then the previous states are important for the next state. So this is where we consider the temporal relationships.
Thank you.
Thanks for the interesting talk. I was wondering on the topic of simulation models and their use for the training of machine learning models. How important do you think it is to use different simulation models for the same class of problems? Or is it possible to just fix one model and then work with that forever? I'm thinking about variability, and I'm thinking about when I hear talks sometimes from people who do simulation, I sometimes wonder, well, what would have happened if you had constructed a somewhat different model that would be exploring different kinds of scenarios? Can you comment on that?
Yeah, there are two parts to this answer. The first part, if we look, let's say, at the same level of representation, if we have different simulation models that arrive to the same result, right, then we don't care which one to use. So this is the first part of the answer. Now the second part of the answer would be more interesting. I think simulation models are very limited in the level of representations that they can be used. So if we use a simulation model to simulate the whole network, and then instead, what we want to do is we want to simulate, let's say, much more closely a certain part of the network, let's say, to understand how water quality changes there and so on. It is very likely that the simulation that simulates the whole network will not be able to simulate in more detail parts of the network. And with our approach, and especially with having an ontological representation, moving between levels of representation is much easier. So in this case, we may need to have different models if we want to simulate different levels.
Okay,
Since nobody had, oh yes, we still have a question. But
So, 1, 2, 3. Interestingly, I work with people in the Netherlands. I work on water, but this is water that people don't want. This is water that comes from the sea, so storm surge barriers. And they do digital twins, and a lot is about control. This is so. I mean, the physical behavior of the water and so forth is not so interesting. They have a kind of predefined condition, and then how to control the storm surge barrier, for instance. This is what they're interested in. And that's why they do everything discrete and so forth and so forth. And they don't use learning technology. Now, I wonder, what is the control part here? How pronounced is it, actually?
When we made this pilot with drinking water network Wittens in the Netherlands, it was very clear that in the pilot that we have, there would be no direct control of the water distribution network because it's still low TRL work. Our aim is to is the work of water engineers that try to understand how to make new models for the system. So it changes the recalibration of these models that they have when they need to run new simulations is a very effort-intensive work. And basically with this work, we can remove this effort. This is one thing. The other problem that they all often talk about is the problem of having incorrect asset description files. So they have a file that describes the network, but there is an error there, or there is some problem, or environment changed since the file was created. And then the simulations that they have are incorrect. So they need to fix the file, but it's not always easy. They need to investigate what is going on and so on. And again, here, this basically leads to causes of the changes, so we can help them to show where the problem is, and they can fix their files faster.
Understood, thank you.
Good. With this, I suggest we thank the speaker again. And I can officially finish this session and pass the microphone to someone who probably has some announcements or some words.
Yeah, not much more to add, just this is the closing of official sessions. We have special subject sessions at 1, which is the trip to the winery. It's at 1, right? Outside here. And thanks again for coming, and I hope to see you all next year.